Hello everybody, welcome back to another Gregorius Maths video. Today I'll be doing Topology 1.2, namely I'll be doing Topological Spaces. But before I get into the video, I want to say a huge thank you and shout out to Black Pen Red Pen, because I won his Black Pen Red Pen Be Like contest, and that made me very, very, very happy. So yeah, thank you, and a very gross shout out to you. Okay. But anyway, topological spaces. Given a set X and a collection of open subsets tau of X, this is a topological space. Topological space if, okay, so X is in X is in this collection of open subsets tau. The empty set is in this collection of open subsets tau. Arbitrary unions. So arbitrary unions of open sets are open. Okay, and finite intersections of open sets are open. Okay, so if you watch my last video on topology, you'll immediately think of open sets when I talk about open. So first off, why don't we look at the real line and tau? Let tau be those open sets which we defined in the last video. We proved this. These two are obvious. Now we're just going to sketch a proof that the finite intersections of open sets are open. Okay. So if we have this collection of open sets S sub I, but it only runs from I equals 1 to n, so it's finitely many. Okay, then that means that if we pick X in one of these, like S sub i's, then there exists a delta sub xi greater than 0, such that the open interval about x minus delta sub xi to delta sub to x plus delta sub xi, okay, is contained in S sub I. Okay, and now if we let delta sub x equal the minimum of these delta sub x1, delta sub x2, delta sub xi, okay, seeing as there are only finitely many deltas and they're all greater than 0, delta sub x is greater than 0, and hence the open interval about x minus delta sub x to x plus delta sub x is contained in here, which is contained in there. Okay, hence it's open. Okay, cool. Now that we've got that out of the way, and we've shown that the real line, along with these open sets which we defined last time, okay, is a topological space. Alright, great. Now, we move on to just one more, very quick example. Let B, for example, equal the set of 0 containing 0 and 1. Now, there are at least two different ways to make this a topological space. The first one is called the indiscrete topology. Okay, and it's defined, and it's where you choose the empty set and the set itself, in this case 0, 1, to be open. Okay, and we can see if we take the intersection, we get the empty set. If we take the union, we get that set, both of which are open. This is open, all the conditions are satisfied. Or we could have the discrete discrete topology. Okay? And the way that we do this is we let the empty set and all of these subsets, well, the empty set is a subset of B, I guess, but all of the different subsets to be open. Okay, and why does this work? Well, if we take the intersection of this and that, we get the empty set which is open. If you take the intersection of that and that, you get the empty set which is open. If you take the union of that and that, you get the set itself which is open. The set itself is open, that is open. If you take the intersection of that and that, you get one which is open. If you take the blah 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 blah, etc. etc. Okay, so basically the indiscrete topology is when you just take the empty set and the set itself to be open. And the discrete topology is where you take all of the different subsets of the set to be open. Okay, that's good. Now we shall define continuity. Okay, a function f from one topological space S to another topological space T is continuous if, okay, for any open set Q contained in T, so the codomain, comma, the preimage of Q under F, so the preimage is an open set in S. So the preimage of any open set in T is open in S. Okay? So, okay, that's good. So now it should be obvious that a function f from S to T is always continuous if if S has the discrete topology. Okay, why? Because the preimage of some subset of T is always going to be some subset of S, but because all of the subsets of S are open, it must be open in S. So basically the preimage of any set in T, okay, will be some subset of S, but because all of the subsets of S are open, the definition of continuity is guaranteed, basically. Or another case is if T has the indiscrete topology. Okay? Because the preimage of T is S, which has to be open for it to be a topological space, and the preimage of the empty set is the empty set, which also has to be open for S to be a topological space. Okay? I consider this to be proven. Alright. Now we take a look at, now we go up a dimension. Let's go to R2. Oh boy, the XY plane. Okay? So if we have some open set Q in R2. Okay? Now, what properties does this open set have to have? Well, intuitively, it can't contain its boundaries. So for every point we pick in this open set, we must be able to construct an open ball around it of some radius delta. Okay? If we had a point on the boundary here, no matter how small I make the ball, oopsie daisy, I went outside. No good. Okay? Oh no, I went outside. See, we cannot construct an open ball around that point. Completely contained inside of Q. Okay? So if we have a point inside this open set, let's call it xy, okay? The open ball of radius delta about xy is equal to the set of all x prime, y prime, such that the square root of x prime minus x squared plus y prime minus y squared is less than delta. Okay? That's how we define it. So now, why don't we take a look at some topological, not topological spaces, some maps which go from R to R2 and R2 to R to check, we've got the correct topology. And I'll leave it to you to prove that this open ball is makes a topological space, makes R2 a topological space, okay? Prove it in a very similar way to how we did it with R, the open set in R, okay? So first of all, let's look at a function which takes in elements of R2 and maps onto R. So the addition map A, which goes from R2 to R and is defined as follows. A of xy is equal to x plus y. Alright, cool. So what we have to do to prove this is continuous is pick some open set U, for example, in R, and prove that the pre-image of U under A is open in R2. Okay, so let's proceed. Let U be open, okay, and let U be contained in R. Okay, now pick some AB to be in U, okay, which means that because U is open, that means that there exists some delta greater than 0 such that the open interval about A plus B minus delta and A plus B plus delta is completely contained inside of U, or that the pre-image of this open interval about A plus B minus delta to A plus B plus delta is completely contained inside of the pre-image of U under A. Okay, that's good. Now, this part here is, if we get a diagram, this part here is the section, but not including, it's the region of space here between the lines y equals A plus B plus delta minus x and y equals A plus B minus delta minus x. Okay, so if we have this point AB, okay, it's equally spaced between the two, and this distance here is delta over square root of 2. Okay, I'm aware that you can't see that, but the distance, this point AB is equally spaced between these two lines, A, B, okay, and because it's a distance of delta over the square root of 2 away, okay, that means that if we let D equal delta over square root of 2, D for distance, okay, that means that the open ball of radius D about AB is completely contained inside of the pre-image of this open interval about A plus B minus delta, A plus B plus delta, which is completely contained inside of the pre-image of U. Oh, look, there's an open ball completely contained inside of the pre-image of U, meaning that A is continuous. Okay, because the pre-image of U, we've just proven that it's open. Alright, good. So, now, if we have the diagonal map, which goes from R to R2. Okay, how do we define the diagonal map? D of x equals x, x. So, as the name would suggest, it looks like that. It's a diagonal map. Alright, now, let U contained in R2, okay, let U contained in R2, okay, ow, be open. I'm sacrificing my knee for you guys, and I've suffered a fatal injury on my palm. So for sacrificing myself for you guys, I think I should, get 1,000 subscribers for that. Yeah. Thank you very much. Okay. So yeah, let U, a subset of R2, be open. Ow. Okay. So, now, if we pick some x in the pre-image of U under D, this means that D of x is in U. Okay? And because U is open, that means that there's some epsilon greater than 0, such that the open ball about epsilon of the open ball radius epsilon about xx is completely contained inside of U. Okay? And now, let delta equal epsilon over the square root of 2. And now this may seem very peculiar, but you'll see why I'm doing this in a second. Now, let y be any point in the open interval about x minus delta to x plus delta. Okay? So, that means that d of y, okay, so now we want to show that the distance, if y is in this, we want to show that the distance between d of y and d of x is less than epsilon, so y is in this open ball here, and then we've proven that U is open, basically. Sorry, the pre-image is open. And basically, you'll see what I mean. Okay, so this means that the distance. Okay, the distance between d of x, and d of y is equal to the square root of x minus y squared plus x minus y squared. Okay, and this is strictly less than the square root of delta squared plus delta squared. And now you see why we chose delta to be epsilon over the square of 2. Because if we square this, we get epsilon squared over 2 plus epsilon squared over 2. That's 2 epsilon squared over 2. That's epsilon squared. Remember, we're taking the square root, so this equals epsilon. Okay? And now, we've shown that the distance between d of x and d of y is less than epsilon, meaning that d of y is an element of U. Sorry, d of y. Yay! D of y is contained in the open ball radius epsilon about x. X, okay, contained in U, okay, meaning that d of y is contained in U, so that means that if we take the pre-image on both sides, that means that y is contained in the pre-image of U under D, but remember that y is in there, so this means that the open interval about x minus delta to x plus delta is completely contained inside the pre-image of U under D. And that shows that D is continuous. Okay, pretend I wrote that down. Okay, so basically if we have this graph here, and okay, we have some open ball here, radius delta. Okay, yeah, you won't be able to see the graph, doesn't matter. Basically, we had a graph here. Okay, we had some graph. This can be the place for the graphs. We had our diagonal map. We had our point here. We had our open ball of radius epsilon. Now when we take the pre-image, okay, of these points, for example, we get the open interval about x minus delta to x plus delta. Okay? That's basically what it would look like. Alright, now, let's bump this up a dimension. Not just a dimension, let's go to n dimensions. So this is some interstellar level stuff right here. Okay? Let's take a look at our n. Okay? What should we define the open ball radius delta to be in our n? Well, the open ball radius delta about xy is equal to the set of all x prime, y prime in Rn such that the distance between x and y is less than delta. Okay, this is the square root of the sum from I equals 1 to n of x sub n minus y sub n squared. Okay, so that's the sum of the distances squared. And on that note, I shall say goodbye. Goodbye.